The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
For work, let's begin here with a definition, and then we'll talk a little bit more about work. Work is transfer of energy. Mathematically, work is given as the dot product of the applied force and displacement. Now, we'll talk a little bit more about the dot product in the subsequent slide. But for now, let's just continue on with work. Now, here's our mathematical equation that we just defined, and the SI unit for work is the joule, which is equivalent to Newton meter, which we also covered in a previous lecture. Okay, great. Now in physics, before we move on to figure 5.0, in physics, in order to do work, an object needs to be moved through some displacement by an applied force. Now let's explore that idea a little bit through figure 5.0. Now we see here in part A, because there's going to be no displacement of this object, there's going to be no work that is actually being done. Now, in object B, since there is displacement for our object, as we see here, right? Thus, work is being done. Now, when the force is along the same line of motion, is along the same line as the motion, right? As we see here, then we can use the equation that's given to us here, which is just work equals force times the change in displacement. And we'll talk a little bit more about that as we proceed through our lecture. Wonderful. Let's now go and do a quick review of the dot product, and then we'll move on to a little bit more, doing more examples with work. All right. Let's get my pointer here. Example, scalar product, or also known as the dot product. Here we're being asked to find the dot product for vectors A and B. So vectors A and B, we're being asked to find the dot product of that. Now, if we just take a step back for a moment, when you have two vectors, right? Two vectors can be multiplied using the vector operation known as the dot product. And whenever you use that operation, it's going to give you a scalar quantity. For example, work is a scalar quantity, and yes, force and the change in displacement, they're both vectors. Now, if you're unfamiliar with vectors, this would be a good time to pause this lecture, go back, watch the lecture on vectors, and then come pick up here. You'll be thankful. Okay, great. Now, there's two ways to actually find the dot product. You can do so through equation 1 or through equation 2. We'll actually go ahead and explore both methods. We'll go ahead and take a look at equation 1 first via the Cartesian coordinate system on the next slide. Okay, great. Let me just get my pointer here. Wonderful. So if we take a look at figure 5.1, vectors here, we see that for our equation, what we need to do is we just need to take the product of the x components of the vectors and the y components of the vectors, and then the sum, and that will give us the dot product. So let's go ahead and do that. So we see the x component of vector A here, right? The x component of vector A is going to be 3, right? But we have to account for direction, right? So that's going to be -3. Furthermore, we see here the x component, or the horizontal component for vector B is going to be 3. Thus, this is just going to be -3 times 3 plus the y component of vector A is going to be 6. The y component of vector B is just going to be 5. Thus, when we go ahead and we multiply and take the sum of the following, we find that the dot product is going to be 21. Wonderful. Now let's see what the dot product would be using the subsequent method that we had highlighted. Perfect. So before we actually move on and solve for this, let's talk a little bit about this equation here. Now, when you see this following notation, what this notation is known as, that's the absolute value notation. And when you have the absolute value notation as such, what that's telling you is we're interested in the magnitude of the vector, meaning the number. Thus, it's going to be the magnitude of vector A times the magnitude of vector B times cosine theta. And theta is just going to be the angle here of 60 degrees.